resume. But I stop recording. I've resumed now. Yes. So we'll be looking at comparison of means. Two means. We're going to see that it's all about two means. Even though if it is one sample, it's about 2 means. Even if it is pair sample, it's about 2 means. Even if it is independent, it's about 2 means. And the non-parametric counterpart. So in a situation where you cannot compare, you cannot use parametric tests. Because t-tests are parametric tests. That is, there's an assumption that the data set follow normal distribution. That's number one. And some other requirement, but the most important is the normal distribution. And the second most important is the homogeneity of variance. That is, in the two sets, the variants are the same. Or even if not completely the same, there's no much difference. There's no significant difference in the variance. Even the mean differ. That is why you are comparing. If you know that the means are the same before, there's no need to say you want to compare if they are, because you don't know if the means are the same or not anyway. That is what you are testing. But even though you don't know if the means are the same, you should be sure before you can use parametric test that the variance or the standard deviation, the variability is the same for the two groups. Now, this is the scope of what we'll be looking at, and at the end of the 3-day, we'll look if we are able to achieve all this. Like, we want to understand the concept of t-distribution. Those are the way we understood the concept of chi-square distribution the other time. No, we actually look at the origin of chi-square. It's the same thing. We're going to look at the origin of t-distribution. Then how you see that all these distribution, somehow, they are related to normal distribution. Just as chi-square distribution is related to normal distribution, because it's actually from normal distribution you derive it. The same thing. T-distribution also has something in relation to normal distribution. Then the t-test to test t-distribution, the distribution is the t, that is how the pattern of occurrence of the value of the statistic, and how to calculate the statistics or use the statistics to test difference between two means, that is the t-test. And then the non-parametric counterpart, in the sense that when in a situation or in situation where you cannot use t-test, the non-parametric counterpart can use. Just like, you know, even though chi-square, everything about chi-square is non-parametric, but there are some situations we cannot use chi-square. Chi-square is not valid. We go for Fisher exact test. You remember? So it's the same thing. If you cannot use t-test because of the assumption for using parametric test are not met, you go for you can rely on the robustness of the test and still do it, or you go for the non-parametric counterpart instead of you transforming the data, because when you transfer, that should be the least option you should take. Then, when we understand all this, we are going to see how you calculate and how to use software to run it. That is the beauty of statistics at this age. Gone are the days where you begin to use hand to solve. How many, especially when you even have bigger samples, how many, you know, you lose value. Like all those days, they say, by that time you be doing group data. You say group me, this thing. In the process of grouping, you lose precision. But thank God for computer. Computer is there, even if the sample size is big, it will run everything together. There's no need for group distribution or group data or all those things that say you are doing group, class interval. Gone are those days. Calculate to do your statistics, class interval. That was when there was no computer. There's no need for class interval now. Apart from you, if you want to tabulate a quantitative result, maybe you want to range it, you can decide to range it on your own based on whatever criteria you want to use. So we're going to see how we run the one sample t-test, independent sample t-test, pair sample t-test, their confidence interval of the mean. Actually, This number 1, 2, 3, they are hypothesis tests. The confidence interval is just by the side. It's not hypothesis test. Confidence interval is a separate form of inferential statistics. So, when we talk about inferential statistics, introduction to inferential statistics, the other time, I made up to the other, there are 3 types, but we usually use 2. There are 3 types of inferential statistics, inferential method rather. There are 3 types of inferential method: hypothesis testing, confidence interval, and Bayesian method. You are done. Bayesian method. The Bayesian method have been there even before the hypothesis testing and confidence interval. But it's not being used. There's some people that try to use it, but it's not popular. So that is the one that talk about pre and post test probability. That's we are not, the people don't usually use it, but most of the thing we do is about hypothesis testing, confidence interval. And you're going to see that you cannot with Kinsey, you cannot be talking of confidence interval with it. No, it doesn't stop you from calculating the confidence interval, because when you do t-test, you compare me, then they match up, because you actually use the mean, the data set, to calculate the mean. That's one different thing between mean and all t-test and all these non-parametric tests. The non-parametric tests, you are not using the value, you are ranking it and now use the rank. So can you see the difference now? In the parametric test, you use the value, but in non-parametric, you don't use the value, but you use the rank. You rank it first, and now use Ozioma. Sorry, just 1 minute. Ozioma.
Children are making noise.
Yeah? Your children?
No, maybe Ozioma's children. You can see, I can hear background.
No, even the Ozioma is not. Ozioma is not talking. He's trying to connect. Don't worry. Even the network is not going. Okay, now let's just move ahead. You're going to see that the non-parametric you are using rank, just rank. Just one funny permutation, the arrangement rank and the arrange, and just say, oh, the smaller statistics, the smaller one is a foreign thing. That's why sometimes we are not familiar with it. So, and to be sincere with you, it is actually easier than the parametric. It's because it's new to, we are new to it. It has been there, but nobody talk about. That's why it look as if it's difficult. It's not actually difficult. Interpretation of results, look at it also. Let's quickly go on. Yes, he has connected. Ozioma, unmute yourself. I cannot hear you unless you unmute yourself. Ozioma. I will remove you. Uzoku, unmute yourself and talk to me. Hello?
Hello, good evening, sir.
Good evening.
Good evening, sir.
Good evening. You are connecting from where? Huh?
Hello, sir. Sorry, the network is poor.
But I didn't have you didn't subscribe. So you didn't subscribe. Why did you join? You didn't subscribe for the weekend something. I mean, you
from
Enugu,
UNTH Enugu.
UMTH. Okay.
From UNTH Enugu.
Okay, but you didn't subscribe for the weekend. The weekend is a pay for workshop, but the Tuesday and the Wednesday is the free one.
I didn't know how to.
So listen. Anyway, unless if you want to continue and you pay later. Unless you want to continue to pay for, because this one is paid for. This is the Tuesday and this that is free. But this is a weekend workshop. Unless you want to
Oh,
continue.
I didn't know, sir. I'm sorry, I didn't know.
Okay. So unless you want to continue and pay later. Okay. Historical background. Let's quickly look at the historical background. Now, in 1908.
Okay, sir. I will join on the Tuesday work. I will join on the Tuesday workshop, sir.
Okay.
Thank you, sir.
Okay.
So she wants to be removed.
Hello. Okay, let's continue. Now, in 1908, a man called Gosset. No, this man was working in Dublin with Guinness.
To be removed. He said she should be removed.
He has removed. Don't mind them. No, they know. They are just trying to. Because me, I didn't change it. I don't like changing my password because if I keep on changing, even the people that pay will even confuse. Sometimes they will forget and they will not be connected. So it's just like a classroom. If you are not supposed to be in the class, why should you come? I just try to see. From the one I started, that's why people started preferring. They are aware. They don't want to pay. They thought maybe, but it's a visual something. I will see. There's no way. It's a manageable number. If let's say we are having more than 30 now, or somebody can just come here. I will not even know. But this is a manageable number. If anybody come here, I know. So, so the man was working in Dublin with Guinness. So he realized that normal Z test, which is the normal distribution. We are not going over the Z now because we are talking about Z before. Even when we're talking of chi-square, I talk about Z distribution, which is the standard normal distribution. So it was standard normal distribution they were using. But he discovered that anything when the sample size is very low, like below 30, even that particular thing that normally follow normal distribution will not follow, the data set will not follow normal distribution. So the Z distribution will not be appropriate for sample size less than 30, smaller sample size. So it was the one that first talked about T distribution. That T distribution has some characteristics similar to Z distribution, but in some way different. So what he realized that sampling distribution of two, in that way you can use this. Okay, I will do
Hello, sir. Hello, sir. Hello, sir. Please, can you help us tell other people to mute themselves? To mute themselves so that you will not be hearing the background noise.
Okay, you know what? Maybe it's me that will take my position. Okay, you go inside because you are using pad. Go inside. My son also is maybe the one making noise because he is receiving Zoom lecture also. So if the lecture just clashed, the teacher they couldn't do their lecture.
Okay, thank you. But there's another person who also unmute apart from you.
Okay. Who is the person? I will dictate the person. But it's only you that is not muted. Yeah. Okay, it's Prof. I've muted him. I've muted Prof. The Prof was normal. So I think it's okay now, right? Dr. Toyin?
Yeah, yes, sir. Yes,
it's
sir.
Okay. Thank you.
Yes, sir.
Okay,
yes, sir.
Thank you. Yeah. So the T distribution is used when the sample size is very small. So you use it to what you're actually using it for is to compare the origin of it, just like the origin of chi-square was this Pearson chi-square. The first chi-square that was described was Pearson. This first T distribution that was described was the one that used to compare two independent groups. So you now look at, okay, the use is a distribution of a difference between two identical observations from normally distributed population. That is, when you look at two, maybe you sample it may be hemoglobin or weight of children or height of children, maybe about 10 of them or 15 of them, another height, another 15. Maybe one from rural, one from urban. We want to see any difference in their height. The distribution of the difference in the height of these two populations is the T distribution. But these two populations are normally distributed. So when you look at the whatever the parameter and the statistic you are calculating, when you calculate the difference, the pattern of occurrence of the difference is the T distribution. It's like normal distribution, but there are some differences in it. Rather than, you see that I'm talking to, I prefer, yes, look at the picture. You will see that the red one is the normal distribution. You know, it's bear shape. But the T distribution also is bear shape, but it's flatter and it has wider base. Can you see? And the funniest thing, the area of under the curve is 1, because area under any curve, any probability density function is 1. That is, any graph that show probability. No, we are talking about continuous probability distribution, discrete probability, any form, either discrete or continuous. Their graph, the total area is 1, because probability cannot be greater than 1. So probability is from 0 to 1. There's no minus in probability. So it's from 0 to 1. So the total area is 1. If you look at the red and the blue, the total area under them is 1. It's only that if the blue has to be flatter, that should that it has to be wider for them to have. It's just like you have something that is elastic. If you have not changed the total content of that thing, but you are changing it, you can make it flatter. But if you make it flatter, the height will go down. If you want the height to go up, it will be narrower. It's the same thing. So you can envisage these two graphs as if they are the same length. Let's say the same length, like a thread, the same length. So if you make it narrower, it will peak. If you make it wider, it will flatten. So the normal distribution is the red one. The T distribution is this one. So you see, it is a family distribution also, just like chi-square, in the sense that there's no one T distribution. No, we know that the standard normal distribution is 1. Just like we know that the chi-square distribution is many based on degree of freedom. It's the same thing with T distribution. There are plenty, many of them based on the degree of freedom. So when the degree of freedom increases, what will happen is that the thing will begin to come up, assuming the shape of normal distribution. And the degree of freedom, we already know, is an entity minus 1. So in this case now, the total sample size minus 1, the number of observation minus 1 for one group, the number of observation for minus 2. If you are dealing with 2 groups now, the degree of freedom will be the number of observation for the 2 groups minus 2. Each of them, the number of observation minus 1. When you now combine the 2 groups, to be the total number minus 2. So you can now say, when you are talking of the degree of freedom, just know that it has something to do with the sample size. That's for quantitative variable. When you are dealing with quantitative variable, the degree of freedom has something to do with sample size. And when you are dealing with categorical variable, not necessarily sample size, but the number of categories. You know, if you are dealing with categorical, like now, if you are dealing with maybe height, no, you are dealing with ethnicity, socioeconomic status, upper, lower, middle. The degree of freedom for social, if there are 3 classes, the degree of freedom is 2. The 3 classes minus 1. If you are dealing with maybe socio-political zone, it's a categorical variable. We have 6 in Nigeria. In geopolitical zone rather. If you are dealing with it, the degree of freedom it will be 5 because there are 6 geopolitical zones. But when you are dealing with quantitative variable, because quantitative variables are there unlimited number of value. So the degree of freedom will be the sample size minus 1. But when you are dealing with category, when you now cross-tabulate, if you look at when you are comparing 2 groups now, the degree of freedom will be 1, the sample size minus 1 for this group, sample size minus 1 for this group. So for the 2 of them will be the two sample size combined together -2. But if it is categorical now, when you now do cross tabulation, when you say geopolitical zone by sex, you are looking at association between maybe geopolitical zone and what do I call it, socioeconomic status, which has 3. Socioeconomic status has 3 categories. The degree of freedom for socioeconomic status will be 2, 3 minus 2. Geopolitical zone, there are 6 categories in Nigeria. The degree of freedom will be 5, 6 minus 5. So if you cross-tabulate the 2, the degree of freedom will be 2 times 5, making 10. Because the number of row, if you put one in the row, maybe the geopolitical zone is on the row, along the row. So the other one along the color, it will be row minus 1 times color minus 1. That is why it will give you 6 minus 1 times 3 minus 1, making 5. That is the way you deal with degree of freedom when you are having categorical variable. But in this case now, it's quantitative variable. The degree of freedom is based on the number of the observation of the sample size. If you are now dealing with 2 groups, most of the time, when independent group, 2 groups, it will be the sample size for the 2 group -2, because each of them will be sample size -1, sample size -1. When you now compare the 2 sample size -2, give you the degree of freedom. So when the degree of freedom, that shows that the degree of freedom for this one will increase with sample size. So when your sample size increases, the degree of freedom increases, then you will see the shape. The shape of the T distribution will begin to look at. Yeah, look at this second one. This one is the one I've just shown. Look at this second one. Look at this is the T, and this is Z distribution, and the T distribution that's approximated Z distribution. Look at T distribution with degree of freedom of 20. Look at T distribution with degree of freedom of 10. Can you see? The 10 is flatter. But if you look at the area under each of them, it's the same. But the other one, the one that is flatter, we have higher, look, it will spread out, wider base. So as the sample size increases, the T will begin to come up, becoming tall like a normal distribution, becoming narrower, taking the shape. So until it reaches, it just build exactly as normal distribution. That's why the degree of freedom now will be infinity. That is when the sample size is large, believing that it's very large. So it will be like normal distribution. So the T distribution, when the sample size increases, behave like normal distribution. You're going to see from this understanding why T distribution is more popular to compare means. When you are comparing 2 means, T distribution is more popular than Z distribution. Even though Z distribution, which is the normal distribution, is the most popular distribution in statistics and research because it is the basis for hypothesis testing. But for comparing 2 means, T distribution is more popular than Z. In fact, nobody uses it. You're going to see the reason. There's no need to use it. Use Z. Look at this. Look at this one, and this third graph here. You will see this is Z distribution, the blue, the purple is the T distribution for the degree of freedom 12, an example. Now, for Z distribution, the middle 95% of the area of the graph is bounded by minus 1.96 and plus 1.96 standard deviation. So that is, if you go to the, you go to the negative side, minus 1.96, go to the positive side, minus 1.96. So the area between the two constitutes 95%. That's the 95% confidence interval. And the remaining area, 5%, will be on both sides. 2.5 here, 2.5 on the other side. That is the level of significance 5% usually shows. So you will see for normal distribution, that middle 95% correspond with 1.96 minus and plus 1.96 standard deviation. But for T distribution of degree of freedom 12, the 95% middle correspond with minus 2.0, 2.201 and 2.201 standard deviation. Can you see the difference? We already said that the T distribution is wider in base, so it's wider. That is why it is like that. But as the sample size increases, it will begin to narrow. So when it reaches anything maybe far above 30 now, you will see that the middle 95% will be exactly like that of the consumed 1.9. It's just like it will just be exactly like normal distribution. Now, look at this graph also. So the fourth one is still describing the same thing. T distribution, Z is the blue, red is T distribution close to 30. Then distribution less than smaller than 30. You know, as it's increasing close to 30, past 30, it will be like normal distribution. So that is the relationship between Z distribution and T distribution. Now, you will not see why, you will not see the reason people now use T instead of Z. Even in comparison, you go to all these things, you won't, nobody talk about Z distribution to compare me because there's no need. You will see the reason. Generally, Z tests are used when we have large sample size greater than 30. The T tests are more helpful with smaller sample size. And that was the reason Gosset invented it. He discovered that for smaller sample size, that Z will not be appropriate. That was how he was able to discover this. That he invented it. I think he discovered it because this thing exists somewhere. It's we that don't know. So the people that didn't know before. So both methods assume normal distribution, both of them. If you look at it, the mean also is 0 and variance is close to 1 also as it's approaching. As the mean of the T distribution is 0, that is that of normal distribution. The variance is close to 1. You know the variance of normal distribution is 1. The area under is 1. The T also, the area under is 1. But as it's approaching, the variance also is close to 1. It is the variance that its variability is higher than 1, but as it's close to normal distribution, it's close to 1 also. So when it approximates normal distribution, the variance becomes 1 also. Like normal. So it look like normal distribution. To me, it's like children now. The weight of children as they are growing, they will be becoming adult. When they become adult, their weight is like that of adult. By that time, you won't talk about weight. Once somebody become adult, you will not talk about weight for age again. For what? He has become adult. So he can have big weight, can have little weight. That one does not now depend on the age. But when a child is still growing, it will depend on the age. I think it's the same thing. Z is more like children, and T like a child. As it's growing, become adult. T is like adult. Now, you will see this flow chart. Do you know if you want to screen, which one should I use for a particular data set? Which one should I use? T distribution or T test or Z test, Z test? This is how to screen. Do you know the population standard deviation? The population standard deviation is required for you to use T test. If you don't know, you can to use Z test. If you don't know population standard deviation, you cannot use Z test. So that is why if it is no, T test. If it is yes, okay. You cannot still use, also you have to now find out you cannot still use Z also until you find out if the population is greater than 30. If the population is not greater than 30, you cannot use it also. You still have to use T. It is when the population is greater than 30 you can use it. So for Z test now, you need two conditions. For the population to be greater than 30, and for you to know population standard samples rather, the sample size greater than 30, and for you to know population standard deviation. So in those two occasions, when the sample size is very small and you don't know population standard deviation, you now use T test. Now, out of 3 options here now, 2 are favorable to T and only 1 is favorable to Z. But there's another thing. Even when you now have population, the sample size greater than 30, at that particular time, Z also approximates Z. T also approximates Z distribution. T is like Z distribution. So in that case, either the population is lower smaller than 30 or higher than 30, say a T distribution would. And that is why, since you can use T distribution anytime, so that you cannot use Z distribution anytime. So why? So, and when you now use, when the Z is a T distribution approximate Z, it gives the same answer also. So that's why you don't hear of the distribution for that. I want you to ask questions because this is not the other class. I want you to ask questions. Before I proceed, we're going to because I just explained the distribution before we now start going to how do you calculate how to do that. Yes, any question?
Yes, sir.
Yeah.
Thank you, sir. Thanks so much. I really appreciate your effort. I just need some clarification, sir. When you told us about the graph, you demonstrated like 3 different graphs using T distribution, set distribution, T distribution, and example. Even the last one, the T distribution, considering the sample size, if it's greater or less than or even equal to 30. Now, my question is, sometimes we talk about this terminology that we sometimes use, leptocuti, mesocuti, plastocuti, and they are important. So I just want to know what is important then with regards to this graph. Where does they belong to, or is irrelevant?
Okay, so you are asking this question now because you were not part of what we have been doing initially when we started descriptive statistics, all those stuff. When we talk about normal distribution, skewness, we talk about this leptocotic and platycotic. Leptocotic just means that something is peak, it's too peak. In a standard normal distribution, if something is normally distributed, the thing will be a bear shape. Then the skewness means it's not symmetrical. Something is skewed if one side is not a mirror image of the other. It's skewed. So the cotic, that is skewness. The cotic means peakness. If it's extremely peak, and when it is extremely flat, and what really causes extremely peak is that sometimes if the variability is very small, maybe the sample size is very high, and the variability of that is extremely small, it will be peak. But when the variability is very wide, and most of the time when the sample size is very small, it will be flat. So the issue there is that that thing actually describes normal distribution, anything deviation from standard normal distribution. It describes deviation from standard normal distribution. So it's used to describe a particular distribution, maybe weight now, or you do even though weight, we know that it's following normal distribution, your own data set may be platycotic or leptocotic. That is, it may be extremely flat, especially when the sample size is very small and the value are wide apart among the people the difference are too much among the people your sample, it will be flat. But when the difference are not much, almost the same for all of them, and the thing will be peak. And most of the time, when you have high samples and all of them are the same, almost the same value, it will be extremely peak. These are deviations from the normal distribution. So the leptocotic just means that extremely peak. The variability is very small. Platycotic is that. So if you look at it, let's say I just want to use to explain. Look at this line graph now. If we are using this thing to explain what you just said now, we will say the red one will be normally distributed, standard normal distribution. The blue one will be leptocotic. The green one will be platycotic. Just for explanation.
Okay, it's clear.
But in this, that one is just telling you, it has nothing to do with t-test or this is telling you deviation from the z-test from normal distribution for a particular variable data set. Do you get the picture now? Do you get the picture? Do you understand?
Yeah, yes, sir. Sorry. I moved there so that you can.
Okay, that's great. Yes, if you want to respond to me, you have to unmute because I will not know if you are responding. Okay, thank you. Any other question?
Thank you, sir.
Welcome. Any other question?
Yeah, I just to ship this in, Dr. Dolapo. Now, when you have quantitative variables and categorize them,
yes.
So that rule, does it still stand that the degree of freedom will be number of categories minus one?
Of course, now, because, you know, if I said something yesterday, yesterday, when we were doing for Thursday's lecture, I said, when you categorize, that thing is more quantitative. If your age is continuous variable, the age group is a categorical variable. Age group is different from age. I don't know if you understand now. So you treat that age group as categorical. So the degree of freedom now depends on the number of categories. I don't know if you understand now.
Yeah, I understand you.
Yes.
Thank you.
It depends on the number of categories. Okay, can we put any other question?
Thank you very much. Yes, sir. Thank you very much, sir. Can you hear me, sir?
I can hear you.
Okay, so I was just trying to like understand the those different distributions that you're explaining. So what it means is that, because I know that the middle is the 0, which is like supposed to be the mean. That's the the mean. So what it means is that when you're having more sample size, you're having a larger number of people in that middle portion. Is that why it keeps changing?
That's why what is changing. I didn't get the last sentence.
That is because, okay, I was saying, sir, that as you're increasing your sample size, it's getting closer. You know that thing you taught us about. I'm just trying to understand if it's the same thing. You know that thing you taught us about when when the sample size is increasing, it will be closer to the actual population. That is the distribution in the So what I'm saying is that the reason why the shape is changing. So you were showing those different curves. So I'm trying to explain that is the reason why it's changing. The curve changed when it was less than 30, and when it was above 30 was because the concentration at the middle increased. Was that why? Since the sample size was larger, the higher number of the
exactly.
I'm trying to understand.
Yeah, you are right. You are right. When you increase the sample size, if you estimate the mean, when you increase the sample size, your estimate is closer to the population parameter. You understand now? But your estimate may not be equal, cannot be equal to the population parameter until you take the whole population. But if you increase your sample, because when you increase your sample size, more part of the population is being taken into consideration. So whatever estimate you get is moving closer to the population parameter. And that is why when the t-test now, when the sample size increases, the degree of freedom increases, the thing is approaching normality. You get it now? I don't know if I've answered your question. Unmute yourself if you want to talk. I don't know if I have answered your question.
Yes, sir. Yes, sir. You confirmed it. Yes.
Yeah. So
yes,
that's
sir.
just.
Yes, sir. Yes, sir. You have.
Yeah.
Thank you, sir.
If you look at it, it's just like mathematics. Statistics is a branch of mathematics. It's just logic. It's for thinkers. You think. But the issue there is that it is thinker that invent. You get a picture. Because most of the thing, it's just like what even the Bible said that what you see, they are function of what did not exist before. God thought of it and said, let there be, it happened. It's the same thing. Even though man will not speak like that, but the man will think also, okay, if you do this, it may be like this. So that's what brings invention and discovery, is thinking. So all these things, the mathematics, if you look at it, when we started, we talk about descriptive statistics. When we talk about summarizing quantitative data, when we talk about mean, mode, median, we now say mean is the most useful among them when it comes to advanced statistics. If you want to move further, if you look at most of the things you are calculating after mean, all this standard deviation, variance, you go to see all these things, even the statistical test you are talking, it's not only about deviation. Chi-square is not about the observed minus expected square. That logic from day one that if you calculate deviation from the mean, if you don't square it, if you add it, it will be 0 because the mean is in the middle. Because it's in the middle, as much part of the data set is below and above. Do you get the picture? So as many that is below is above also. So when you now remove mean from each of them, those ones that are less than the mean will give you negative sign. Those ones that are equal to the mean will give you 0. Those ones that are more than the mean will give you positive when you remove mean from mean. When you try to, the negative, if you sum all the negative and sum all the negative, they are equal. When you now start to add everything, it will be 0. And that was why the thinker said, okay, the only thing that can make us to go further is to square the difference. Knowing that when you square, you remove the element of negativity. That was how they square. And now, that was how they got variance. Divided by the degree of freedom, called variance. Square root of since you have squared before, you want to come back from where you started, you now find square root. That is standard deviation. Can you see? And when you look at all the statistics between chi-square, the theta you go to see is, in fact, by the time we get to ANOVA, and that was analysis of variance. It's the same thing. It's about sum of square. It's about just logic about this mean, the mean minus x square. Everything about statistics is just about that. Go to all forms of statistics, just different way or the other. Playing with number, like algebra. That's all. So a combination of algebra and calculus. That's what we have in statistics. So let's proceed. If there's no other question. Yes, I think we are through with this. Now let's move. Formula for statistics. I say I wanted to change this thing. I'll say it's computation. Now, here we have understood at least something about the distribution based on what we knew about normal distribution. We understood T distribution. Now, this T, how do you calculate it? Test statistic. T is a test statistic. Just like the way chi-square is a test. All of them. Either Z, T, F, we're going to do in ANOVA is F. All of them is the same logic. They are the same thing in different name. Just like you say somebody, you go to Ebola and say Eze. You go to Ebola and say Oba. You go to this way, Emir, whatever. It just means the head. It means the same thing, but in different languages and the faction, the way they go to different places, even all over the world. The same thing. So it is this T-test now, in fact, is the easiest to understand hypothesis testing. The easiest T-test. That was why I was surprised because I believe that it is easier to conceptualize T-test than chi-square. It is easier, far easier to conceptualize T than chi-square. Chi-square is more popular in the sense that many people, because people do it categorical variable, even when it's they can categorize it and just run chi-square. So even undergraduate, when they first hear of statistics, if there's anything, it's chi-square. That's all. You leave the rest for them. For undergraduate too, it's chi-square. Even for postgraduate, the first thing everybody will is chi-square, and that is why people assume it's easier. It's not even easier. Even T is easier to conceptualize than chi-square. Now, the logic behind all hypothesis testing is that you are looking at the difference between what you observe in your data set. And you say, what you observe in your data set, what I can see. Like for example, now, I did blood sugar. I say, maybe I have two groups, 30 male, 30 female. I did for male. The mean blood sugar for all these people is maybe 60. I did for female. The mean blood sugar for all these female is 65. So the observed values are 60, 65. And the observed difference, observed value also, the observed difference is 5. 65 minus 60 is 5. The observed difference is 5. All of them, anything you can see in your data set. And you know that data set is from sample. It does not take all the population into consideration. It's only your sample. And now you want to see in the population, how is it? This difference I've got, you know, these 5, is it the same thing in the population that the difference between the blood sugar between male and female is 5? The average blood sugar, if you can take all the male in the population, our adult male in the population, and do their blood sugar and calculate the average and do the same for the male, are we going to say that in the population the difference is 5? Then are we going to say that that is how it is if we do this study another time? It will not give you a different thing. How we should have 5? It's not by chance that it just happened that it's 5. We do it again, it can be more than 5, it can be less than 5. In fact, you can even do it again and see that the average blood sugar for male is higher than that of female. After all, the average for male is 60. But there are some male that will even have blood sugar greater than the average for that female. Greater than some females' blood sugar, like even greater than that 65 that is the average for the female. And there are some female also that may even have blood sugar far less than the average for the male, far less than male's blood sugar. But it just happened that the average for them are what you do for each of the group and what you have just seen. So the statistic is to test what is the probability? What is the probability that this result, this observed value I've seen, that is due to chance? That is just a chance occurrence. If it's a chance occurrence, that shows that there's no true difference between, that shows that we cannot say that the blood sugar of male and female are different. This difference is just a chance occurrence. The probability. So now the statistic will quantify that thing, and the p-value will give you the probability. What does the statistic quantify? Now, the intelligent people now keep, okay, what they want to quantify is the difference between this observed difference, the observed value I've observed, and the hypothesized value. What is the hypothesized value? Hypothesized value is the value it should be if there is no difference. You know, you are testing hypothesis. The hypothesis you are testing that, oh, there's no difference, no hypothesis. Say there's no difference between the blood sugar of male and female. I'm just using as an example. No hypothesis, there's no blood sugar between male and female. Can you hear me now? The thing just went up.
It's back.
Yeah, we can hear you now.
This just fluctuates. Yes, the alternative hypothesis, see, there is a difference. Now, in the no hypothesis you are testing, I think we have talked about that before. There is no hypothesis you test, it's no alternative hypothesis. So that no hypothesis, there's no difference. If actually there's no, if it is true, what should be the value? Now, you are looking for difference between two things, 60 and 65. How did you get the difference? You remove one from the other. So if actually there's no difference between their value, they will have the same value. And when you remove one from that, it will give you 0. So
hello, sir.
Yes, sir.
Sorry that I have to interject. I just want to get something clear before I forget or before you go far.
Okay.
You just make a categorical statement, so to say, that it is the no hypothesis you test, not the alternative.
Yes.
I was thinking the third question that need to be answered.
Well, the research
for example, when they say there is relationship between height and weight or a particular group, and the alternative now say there is relationship. So I may be confused. I'm not too
okay. Let me explain. Yeah, let me explain. I understand what you are saying. You know, because most of the time in research, you want to find something. But people have forgotten that not finding something also is finding. If there is no association between two things, it's a finding also. No, that's the problem we have with our environment. Where it's not only our environment, it's only that is more prominent here, all over the world. If you do research and you didn't find anything, any relationship between two variables, in fact, if you want to publish it, they will not likely take it from you. There is a finding. So it is when you find something, you are likely. Even if you go for exam, if you do research, if you didn't find anything, you will not say, okay, all this your effort is wasted. They will likely fail the person. But the person have to cook and say, I have found something. So that is the mindset. Now, yes, we know that we are looking for relationship between two things. What we're actually looking for is there a relationship between these two variables or not? It's not as if maybe we are looking for a relationship. I don't know if you understand me now. Is there a relationship or not? Negative finding is a finding also. It's just like Thomas, when after he has performed 1,000 experiments, he said, don't be discouraged. We just knew 1,000 ways that will not work. You don't bother about it again. You look for another way. So negative finding also is a finding. Now, to now answer your question properly, your research question is stated in two mutually exclusive statements. That your research question is stated in two statements. The first is null, and the second one is alternative hypothesis. The null hypothesis says there's no difference or there's no association between this variable and this variable. No association between blood pressure and age, or blood pressure and sugar in salt intake. Then the alternative hypothesis says that there is an association or relationship between blood pressure and the salt intake. So if one is true, the other one will not be true. They are mutually exclusive. Mutually exclusive means that if one is correct, the other one cannot be correct. Any of them will be correct. There are two. Which one of them, A or B? It's like a dropping, tossing a coin, head or tail. It's either head or tail. That is these two statements are mutually exclusive. Why you do not test alternative hypothesis? This, if you say there's a difference between my age and your age, the next question will be, what is the difference? So if there are infinite number of ways, my age will be different from your age. It can be different by 1 day, 2 days, 3 days, 4 days, 1 week, 2 weeks, 1 year, 3 years, 4 years, 4 years, 1 hour, 4 years, 2 weeks. You see infinite number of ways. Two things can be different. So for you to now test it, you have to now go and test infinite number of alternative hypotheses. But if I say there's no difference between my age and your age, there's no difference, it's the same. So it's just one. And that is why the alternative hypothesis is not tested. The null hypothesis that is tested. Have I answered your question? Have I answered your question? Unmute yourself. You remember. Okay, you are okay. That's great.
Yes, sir.
Okay, that's great. So now, here, observe value. What you observe difference between the two groups minus. You want to see, is there any difference between the observed difference and the hypothesized difference, which is hypothesized value. And the hypothesized value say there's no difference between. So look down. Can you see the numerator of this formula is the same thing repeated here? Let me bring the numerator here is the same thing here. So the observed value is x minus L2. That is the difference between the two mean, the two groups we are looking at. Then this mu1 minus mu2 is the value. No, these are the value, this x1 and x2 are the mean of each group. So s1 minus s2 mean the difference between the two groups. Then this mu1 and mu2 mean the hypothesized value, that is in the population. This is the value, this is the value for this group, this is the value for this group. If no hypothesis is true, that mu1 minus mu2 will be 0 because mu1 will be equal to mu2 if no hypothesis is true. The hypothesized value will be 0. And that is why if you now go down, this part of the formula is out because it's 0. So when you are writing t-test formula for two groups now, this is what you write. Okay, I have not discussed the denominator, but I'm just talking of the numerator. Can you see now? The numerator now, this section of the numerator is out because it's usually 0. The hypothesized difference is usually 0 because it's the difference, is the value when no hypothesis is true. If the value, whatever value, no, it will be this. If it is 97 here, it will be 97 here. When you remove 97 from 97, it will give you 0. That is why that one's out. Now, what is look at, when you now look at the difference between the observed and hypothesized value, it's not just the difference. What if we find a difference between observed and hypothesized value? It's not just the difference. You want to divide it by the standard error of the value. If you remember, when we talk about inferential statistics, we talk about standard error. And we say standard error. Let me share that. I just, it's good to share that slide with you. That slide on where I talk about standard error. For you to understand the concept of standard error. I know some of us were not there when we first of all explain those things about standard error. Let me just 1 minute, I will share the slide on talk about standard error. I think it's under inferential statistics. Introduction to inferential statistics, yeah. Yes. Yes. Let me share it now. Yes, standard error. So we talk about, yes, standard error. Before we get there, what we explain is that they talk about, when we talk about sampling distribution, I don't know if any of us, how many of us were around when I discussed sample distribution. I know Dr. Joy has been following from the beginning. That's true. I lecture from the time. Prof, I don't think Prof follow us from the beginning. Ugo, I think you have been following from the beginning. Yeah? I want you to unmute yourself and talk. Who has been following our lecture from the beginning when I started talking about descriptive statistics in the beginning?
Yes, sir.
Yes, you have been, Ugo, have been following. Dr. Balogun has been following. But,
yeah, you are right. You are right. You are right.
Yes, sir.
Yeah. Prof, has Prof been following? No. Prof, but Dr. Isaac has been following. It's like I've been seeing it. Because number one, he's the one I usually first of all log in and be waiting. I usually see. So Toyin just joined recently. Now, the standard error, when I talk about sampling distribution doesn't mean that you take sample many times. If you take sample many times, after taking maybe sample maybe of 20 people or 100 people, but you do it many times. Many times when you summarize it to get your maybe mean or percentage or whatever, you get different statistics because there's variation. If you take sample from the same population now, Now, you calculate, you say their mean is 30. If you take another one, you may not get exactly 30. You may get 31 or 20 something. If you take another one, you may not get. If you continue taking, you may repeat, get 30 also many times. So there's sampling variation. So if you continue taking like that, you take for many times, that particular, the statistic also follow a pattern. That is the sampling distribution. Because it gives you different value, you have recorded values. Each time you take the sample, you can add all the value together and calculate average. When you calculate average, the average, that is the mean. If it is the mean that is your statistic, maybe it's the mean you have been calculating for each of those samples, you are calculating, maybe you took sample 150 times. You have to gather 150 means, add it together, divide by 150. It will now give you, you are calculating means of the mean. It is believed that that means of the mean will be equal to the parameter in the population. That is the logic in differential statistics. So the sampling distribution is just to give you a concept that whenever you take some many times, if you now calculate average, that average will be, it should be closer to the parameter, because you know that the sample you take may not be, is not equal to the parameter, since you have not taken the whole population into consideration. You have not sampled the whole population, you have not taken measurement from the whole population, you only take sample. So whatever you have is an estimate of the population parameter. But when you, if you not take the sample many times, when you get that estimate many times, now calculate the average of it. It is believed it should be closer, it should be the value of the parameter in the population. The people in the lab, they do it now. When they take measurement, they take measurement, the same measurement 10 many times, 20 times, and now calculate the average, believing that that average should be the real value of that measurement. Now, you know that this thing has a pattern you have taken, calculated. If you calculate the mean, you can calculate the standard deviation also. That is how deviate, how vary, what is the variability between all those different sample statistics and the mean of mean you have calculated. So the standard deviation of sampling distribution is called standard error. You get it now? The standard deviation of sampling distribution is called standard error. And it is believed it is equal to the standard deviation of that attribute in the population. And that is why some people say, what is standard error? They say population standard deviation. It's not true. It is just equal, believe that it is equal to the population standard deviation. Standard error is a standard deviation of sampling distribution. But it is believed that it is equal to the standard deviation of the attribute of the population. This thing we are saying is applicable to both quantitative and qualitative variables. You know the reason? Even the qualitative variable that sex, geopolitical zone, ethnicity, all this, anything categorical, when you summarize it, it's not in percent, in number, you summarize it, you say 50%, 20%, 30%, 20%, 20%, 30%, they are numbers. Do you get it? That is why they call that type of research quantitative research. That's how it gets its name, because you end up, either you are dealing with qualitative variable, categorical variable, or numerical variable. When you summarize it, it gives you number. If it is quantitative variable, numerical variable, you are summarizing, you summarize it with mean, standard deviation, mode, media. If it is categorical, you are summarizing, you can write with percentage. Whichever way, either mean or percentage, is number. That's why they call it quantitative research. So the number, even for the categorical variable, if you take sample many times, that number it give you, if you take sample 150, it give you 150 percentage numbers, which you can calculate the mean. When you calculate the mean, it is believed that is the percentage of that attribute in the population. Then you can calculate, since you calculate the mean, you can calculate the standard deviation of those statistics. The standard deviation is standard error. So you can have standard error of proportion. You can have standard error of mean. So now, I want you to know two things about this standard. Okay, before I say that, look at this illustration I usually use here. Look at this, just to illustrate the standard error for you. look at this belief that let's say this is household, different household in the population. The number of children, we are looking at number of children in the household. In the population, let's say the real parameter, the average number of children is 3. That will have to be a high socioeconomic community, population, high socioeconomic, like you people that don't want to have many children. And the average children will be 3. Now, in the population, let's assume, as is written here, if you take sample, this person takes sample of 4 households 9 times. When he did it, he calculated the average number of children. So for this sample, the average is 3. For this sample, the average is 2. For this, okay, let me include the notation because for this, can you see average is 3 here, average number of children is 2 here, average is 4 here, average is 3 here, average is 1 here, average is 4 here, average number of children is 3 here, 2 here, 5 here. If you try to now plot how many have 3, how many have average 2, you see only one has average 1, 2 has average 2. Look at this and this number of children. 3 have 3. Look at it. 1, 2, 3. Then 2 has 4. 1, 2. Then 1 has 5. Only this one. So if you try to plot it now, you see that it goes up and comes down. So I think it's really that one also follow normal distribution. That is the furtherance of this, because that is where the central limit theorem comes from, which we also discussed here on this slide later. After the standard error, the standard central limit theorem. He's saying, irrespective of the type of distribution you are dealing with, either that thing is binomial, something that don't follow normal distribution, either is chi-square that is skew, either is Q or Q to the right, Q to the left, or it's not even normal distribution before. They are sampling distribution follow normal distribution when you increase the sample size. That is, you do originally the data set, they don't follow normal distribution, but they are sampling distribution. I think you understand the meaning of sampling distribution. It's not the distribution of the data set. It's the distribution of when you take the sample many times, the statistic you calculate, the variation, the way it varies, it follows normal distribution. If it is sex, you are able to do it. Because you end up saying, oh, the percentage of female is 24, 30 something. So it's number to give you. At the end of the day, if the sample size is large enough, the sampling distribution will follow normal distribution. That's what the central limit theorem says. This is what you now say here. So that is why normal distribution is the basis for hypothesis testing. Now, come back to that standard error. You will now see the mean is 3. This sampling distribution, the mean of all of them, if you calculate, add all of them together. If you add and divide by 9, it gives you 3. If you look at it, let's add all together. 3 plus 2, 5, plus 4, it gives us 9, plus 3, 12, plus 4, is it 4 or 1? Yeah, plus 1, 13, plus 3, yeah, 16, plus 4 is 20, plus 2, 22, plus 5, 27. Divide by 9, because there are 9, 1, 2, 3, 4, 5, there are 9, it gives you 3. So can you see, the average now is 3, and the value of average in the population is 3. It's just illustrating the logic behind this sampling distribution and the standard. So the standard, if you now the mean is 3. If you now look at the standard deviation of each of them, how you remove mean from each of these mean, their mean, which is 3 from each of them, if you and calculate the standard deviation, it will give you 1.22. So the 1.22 is the standard error, which is the standard deviation of the sampling distribution. The mean is believed to be the mean of the sampling distribution, is believed to be equal to the mean, the real parameter, mean we are looking for in the population. Then the standard deviation of that sampling distribution is called standard error. What is the usefulness? 2 things. If the standard error is very wide. It's large, it's big. It may show two things. It may show that the attribute, they are far apart in the population. They are different. If you compare height and weight, height is closer in population among people than weight. Weight very more. If you compare income, income is one of the things that vary most in the population, because the income very more. You go in Nigeria now, some people per month, they are not any more than 1,000, 5,000, 2,000, what they are making per month. Some people are making 30,000, some people are making 90,000, some people are making 1 million, some people are making 10 million in a month, some people are making more than that in a month. So you see the variation in income is one of the widest. So in that case, the standard error for, if you calculate for this for income, it will be very big because the variation is very large. Something like height that don't very much among people, the standard error will be small. That is one way of interpreting it. Another thing about standard error, if the standard error is very wide, is very large, it means that your estimate in your sample is too far, is far from the population parameter. And if your standard error is very small, it means you are more precise. Your estimate is close to the parameter. And you know, in research, you want your estimate to be close to the parameter. You will desire for your standard error to be small. Now, how do you reduce standard error if you want it to be small? Now, intelligent people have found out that nobody takes sample 100 times and say they are doing sample distribution. They were doing it before. And when they were doing it, it's not as if they were doing it the way we are doing it now. The statistics started with all these gambling people. I don't know if you have heard of Monaco, Monte Carlos in Monaco. It's a French, it's one principality, French principality. It's one small country. It's not, in fact, it's not more than, in fact, it's not up to Vatican City. That is the country on its own. It's not up to Vatican City. It's very small, along the beach. What they do there is casino. That is where these statisticians were going to collect data. No, all this gambling is there. Nobody has go. In those days, nobody, the way people that invented certain statistics, nobody do survey and say it's going and say, oh, we are doing a study. It was not common. So they go to casino to get data. Then many sample now, you see the same type of lottery. When they do many times, they can get that type of thing. But now they have also discovered that no, you don't even need to take sample many times to understand sampling distribution to calculate standard error. All you need to do is to calculate, just take your sample once, calculate the standard deviation, and divide by square root of sample size. Look at it. The denominator is square root of sample size that is the denominator now. That shows that when you increase sample size, it will decrease your standard error. If the sample size is reduced, of course, your standard error will jump up. So if you want to be, and we already said that when your standard error is very small, it means that you are more precise. Your estimate is closer to the parameter. So in that case, if you want to reduce your standard error, you want to increase your level of precision, you increase the sample size. Because it's the denominator there. When you increase the sample size, it reduces your standard error. So standard error, I've told you of two things. It shows how the variability of the attribute. The second is that it shows how precise your estimate is. Now, I want to go back to what we were discussing before. You will see now, when you now look at the difference between your observed and your expected, you want to divide it by the inherent variability. What is the inherent variability? What shows the variability? What is the measure of the variability of the attribute in the population? Is the standard error. We know that when the standard error is very small, it means that the attribute does not do very much. But if it's big, the very much. So now, imagine you do your different, observe different, and your hypothesize different. It look big to you. This different I'm seeing. The blood sugar of male is higher than that of female. I can see the difference. But before you can say categorically that it's not due to chance, first of all, divide it by the inherent variability, which is the standard error. I don't know if you understand now, because we know that if care is not taken, what you are seeing as different may not be different, because I've already told you ab initio that even we are saying that the example I use, the blood sugar among the male smaller than female. The average blood sugar for the female 65, male 60. Then you may see some female, even though their own average blood sugar is 65 higher. There are some females that have lower blood sugar than some men. There. And even some of them even have lower blood sugar than the average for that man. There are some men also that have higher blood sugar than some women. And even some have higher than the average for the men. So you have to look at how vary that particular attribute. If attributes vary much, if the attribute vary much in the population, something that look big, different between observed and expected will not be significant, because after all, in the population, the thing vary. That type of difference is observed even among general population. So that is why the intelligent people, let's divide the observed minus expected. Expected is the hypothesized. Another way of saying hypothesized value is expected value. Observed minus expected. Let's divide by this inherent variability. If the difference you observe here is the same thing as inherent variability, when you divide, it give you 1. That shows there's no even difference. There's no difference between there's no association. There's no difference between the two groups you're dealing with. But if the inherent variability is smaller than the difference you have observed, because the inherent variability is the denominator. If it's smaller, when you divide this by this, it will be greater than 1. If there is much different, really different, it will not only be greater than 1, it will be far, far greater than it will reach a critical level. And that's this one is more than the critical value. This difference is not due to chance. It's a really different. But there are some situations, you even see that the inherent variability, the standard error is even bigger than the numerator. That shows that it cannot be any different. That shows that the difference you ever see is chance, pure chance. That is the logic. You see the logic behind hypothesis. That is just the logic behind all hypothesis. If you remember, chi-square, you know, observed minus expected. The expected is the hypothesized value divided by the observed. Then you may begin to question why did it divide by the observed. But this one is clearer. The detail is clearer because it's dividing it by the inherent variability. Somebody asked a question before we move for that, because you need to understand the concept. Somebody wanted to ask a question.
Yes, I wanted to ask about because you were explaining the last part about where if it's greater than 1, you were explaining that I didn't get that part. But anyway, the first question I was trying to the last part we're talking about. That's where that formula about observed minus the hypothesis value divided by the standard error. There was something you now said that if it is greater, that is why the variability is greater than 1, far, far greater than 1. I didn't get that part. Then the second question was, that diagram you showed. I understood the part about the means of the mean. But I was trying to I'm just understand that concept. The one for how the standard error fits in there. So would it now be the standard deviation of each of them, each of those different, that diagram you showed?
Yeah.
So what I was trying to understand.
Okay, I will attend to it. Does anybody has any? Okay. You are not true, right? You are not true.
No, that's all, sir. Thank you, sir. No, that's all.
You're welcome. So does anybody has anything related to that? So that I go and explain everything together. Any question related to that also? No question, right? Okay. Let me go and explain that. see? Yes. Now, what we just say is that this one is just an illustration. This is the population. 3 is the mean of what you are looking for in the population. Is there. That is, if you take all the number of children in each household in the whole population and divide by the number of households, it will give you 3. Mean that the average number is, it doesn't mean that some households will have less than 3, some will have more than 3, but the average value, the mean in the population, which is mu, that is the parameter which you don't know. It's only God that knows. But you now take sample. Just as this person takes sample 9 times. 9 times takes sample of 4 households and calculate the average number of children in those 4 families and give this value. So what we are saying that if this is just like you take sample, your sample of 200, just like this, it's only that this one just 4. So imagine your work now, you take sample 9 times and you calculate different averages, you get your summary is different. But of course, some of them concise because we have one that are 3, 3, 3, some are 2, 2, some are 4, 4, one is 1, 5. So some, but there are variations. Some will be similar. So if you now add all the mean, the average for the 9 together, and now calculate the average, it is like you are calculating the average of the average now. That average of the average, it is believed, if you look at it, is equal to the parameter, because when we calculate the average, when we add all of them together, the 27 will now divide by 9. It gave us 3, and 3 happened to be the mean in the population. So that is why it is believed that when you do your sampling distribution, whatever, you now calculate the average of your statistics. Statistics mean that the summary you get. You know, the summary of sample is statistic, while the summary of population is parameter. When you are interested in the parameter, which you don't know, when you, let's say you take sample many times, you get different statistics. The average of all these statistics is believed to be equal to the parameter. And I give an example in the lab. Even the people that are astronomers, they are studying planetary system, they use their telescope, they want to know the distance between 2 planetary bodies, they will try to shoot it many times. When they do it many times, they now calculate the average. They now say, okay, the distance between these 2 planets is this. So they do the same thing. In the lab, people measure something many times, now divide by the, when divided by the number of times they are measured, they say this is the average. Believing that that average will be the because of some value will be higher than that, some value will be lower than that. They calculate the average of all their reading and say this should be the real, close to the real value. It's the same thing. So the mean of the mean. But we say the mean of the mean because we are talking of the mean here. Sometimes your statistic may not be mean, it may be percentage. The mean of the percentage. So far is number, you can calculate the mean. So the mean of the percentage, you get it. It is equal to the real percentage in the population, real parameter in the population. That's one. Now, because all of them, they have different value, as you can see, and you have calculated mean. You can calculate, use the mean to calculate standard deviation. That is how deviated each of them is from the mean. Like all this one are 3, 2, 1, 4, all those. We can calculate their deviation from the mean, which is the 3. When you calculate their deviation, when you calculate their deviation, you now calculate the standard deviation, you get 1.22. That standard deviation of the sampling distribution, it is called standard error. Standard error is a measure of the variability in the population. That is, if the standard error is very small, it means that that attribute is not too different in the population among the subjects. The difference between one subject from the other for that attribute is not much, like that of height now. Human beings we don't differ much in height compared with weight. People differ when it comes to weight more than height. So you can see that the standard error of height is smaller than the standard error of weight. So the standard error, That's one thing about standard error. The second thing is that if your standard error is very small, it means that your attribute, what you have calculated in your statistic you have calculated, is close to the population parameter. If your standard error is very big, it's a little bigger, it means that your attribute you have calculated, that thing you calculated is far from parameter. And that is why, and I also say that nobody go and go to take sample many times because you want to know standard error. So you are doing sample distribution, because intelligent people have found out that the standard error is standard deviation divided by square root of sample size. You just take sample 1, then calculate the standard deviation divided by square root of sample size. What it means that if your sample size increases, it reduces your standard error. As you increase the sample size, your standard error decreases. I don't know if you grasp it, and that is why when we talk about your increase your sample size, when you increase your sample size, if it's related to what you asked the other time about the normal distribution. As the sample size increases, you will see that the T approximates Z distribution, and you say that the attribute is now getting closer to the parameter. So that is why they now use the standard error as a measure of variability, inherent variability in the population. So standard error is a measure of inherent variability. Now, when it comes to what we are saying, when it comes to test statistics. So when it comes to test statistics now, standard error now is the measure of inherent variability. That's why when you want to now say, okay, I want to know if this difference is there, you now divide the difference in the observed and unexpected by the standard error. Because if the difference is as big as the standard error, they are equal. That shows there is no difference. If you divide 30 plus 30, 2 plus 2 divided by 2, it will give you 1. If the numerator and denominator is the same, if the difference you have seen in your study between the two groups is the same thing as the standard error in the population, there is no difference, because when you divide the 2, it will give you 1. It just shows that whatever difference is just due to chance. But for you to see that the difference is really 1, the numerator should be far, far above the denominator, which is, that is, the difference you are seeing should offset the inherent variability, which is measured by the standard error. Does it make, is it clearer now? Yes. So any other one. So now, it is very clear. The only thing now I need to explain here is this formula that look funny to you. The lower part of the formula. This is the standard error. Don't let it be. Let me just jump and go to when you are. Can you see? If it is only one sample t-test, this look at standard deviation over square root of sample size. That is the standard error for you. Can you see the formula? Standard deviation divided by standard deviation of the sample S divided by square root of sample size. That is the denominator. Why this one is like that is because there are two groups. So it's just mathematical operation they did there. What is there is that the standard error, that is S all over standard deviation S all over square root of N1 plus standard deviation of this second group over square root of R. But because they want to bring this square root over all of them, because the square root is supposed to be for only the denominator, the sample size. But because you are 2 now, if you want to expand the square root over all of them, all you need to do, you have to square this one that doesn't have square root before. That is where this S square for both of them come. So it's the same formula. So this one, the denominator is just the square, is the standard error of the difference between the two groups. You may not, but just for you to understand that the computer will do everything for you. You are not going to be solving unless if you are still doing your MPhD, they want to, or you are doing PhD, they still want you to be solving with hand. I see, but to me, it's better you understand it, and if you see also, it's very simple. Once you can conceptualize it, the matter of just put the value you get. So that is why look at this formula for the independent T. So from this now, you're able to conceptualize hypothesis testing. Now, let me just quickly discuss the assumption of parametric test. Now, the T tests we just described, they are parametric tests. The parametric tests are tests that are carried out with an assumption that the data set follow a theoretical distribution, normal distribution. Because parameters from parameter, you remember, attribute of population is parameter. So when you say parametric, it means that there is an assumption that in the population, this variable are measured, the value follow a pattern in the population, follow that normal distribution. That's why they call them parametric tests. So T test is one of them. So T tests, they are parametric tests. But what are these assumptions? The assumptions, what are those things that must be met by your data set before you can use parametric tests, which T tests are. Because if you cannot make those assumptions, you have alternative to go and do the non-parametric counterpart, which we are going to discuss later. Normally distributed data. These 4 parameters, the criteria rather, they are arranged in order of importance. The most important is number 1, followed by number 2. The least important is number 4, followed by number 3. Normally distributed data, yes, homogeneity of variance. That is what it means by homogeneity of variance. The group you are testing, you are trying to test the 2 groups, even though you are testing the mean, if the mean is the same or not, their variance should not be different. It should be the same. Even if it's not the same, but it should not be significantly different. So the variability among them in each group should be the same. Because if it's not like that, it will affect the reading. Sometimes you will see that you are comparing 2 groups, you discover that the 2 mean are extremely close, and it's still significant because their standard deviation are different. One is far, one maybe have a similar large standard deviation, while the other one has small. So that's that variability is not the same among the two. It's not appropriate to use because it will not give you false impression. It will not tell you that something that is not significant is significant. So that is why. So you see, I don't know if you have seen something that you see the mean, it's very close, it's significant. Because if you go and check the sorry, I'm back. Didn't just went off. Can you hear me? Can you hear? If you hear, somebody should just indicate. It's working now. Hello? Somebody should unmute and indicate. If you can hear. Unmute yourself and talk if you can hear me. Hello? You can hear me, right? They're just looking. If you can hear me, talk now. Unmute yourself and talk.
Yes, we can.
Yeah. Okay, that's what
we can.
We
can hear you.
Okay.
Just back. Yeah. Just back now.
Okay.
Yeah, it's when.
It's off again.
And
off again, no.
Yes, I'm back. I can hear you.
Yeah, off again.
Yes, I'm back. I'm back now. Let me see. Let me use the MTN, Jerry. This is your year. Okay. The MTN comes, I'll just join. Okay, you can hear me now. Let's just. Yeah. Okay, let's continue. If the MTN come, I will join it. So the most important, okay, normally distributed homogeneity of variance. I've explained that. So when you find a situation where you find that two means are similarly close and is still significant, it may not be appropriate. So it's better you may not be appropriate using parametric test, because the homogeneity of you will see if you check the standard ratio, you see one that is extremely large, while the other one is small, appropriate. So with that, you know that there's no homogeneity of variance. When you want to run the t-test with SPS, it gives you, by the time you go to do, you see, it alerts you, it does the homogeneity of variance for you. So data must be measured at least at interval level. Interval level means, remember our scale of preference, a scale of measurement, nominal, ordinal, interval ratio. So, nominal and ordinal is for categorical. You can see give number to ordinal, you can rank it and give number. But interval and ratio is for quantitative variable. So that should be quantitative variable. So all these things you are ranking, you have to, if it is ranked something, better you use non-parametric. So if you use Likert scale, use some, unless if it is aggregate score of the Likert scale. But if it is the raw score 1, 2, 3, 4, 5, and then the sample is very small, it's not appropriate to use. But if you look at it, it's number one.